Okay, let's talk cosmic ice. For decades, we've pretty much understood it as this kind of chaotic, structureless jumble of molecules.
Yeah, that's right. The universe's most common form of water, just frozen solid in a truly amorphous state. That was the picture.
But what if that really bedrock assumption was just completely fundamentally wrong?
It's an amazing thought, isn't it? And there's this new research effort that is, well, literally redefined what we thought we knew about ice,
Hmm.
right down at the atomic level. It's turned decades of scientific understanding kind of on its head.
That really is incredible. So, for this deep dive, we're going to unpack this groundbreaking discovery.
Yeah, let's get into it.
We'll explore what this revelation means for, well, everything from how planets might form,
To the evolution of entire galaxies.
and maybe even down to the tech we use right here on Earth.
Exactly.
So get ready for some, I think, truly surprising facts and maybe a completely new perspective on something as, well, as common as ice. So to really appreciate just how big a deal this discovery is, maybe we should quickly touch on water itself. I mean, its properties are pretty peculiar, even here on Earth, right?
Oh, absolutely. Water is famous for not behaving like other liquids. It's quite unique. And scientists have actually identified, get this, over 20 distinct frozen phases.
20. Wow.
Yeah, under different conditions, pressure, temperature, you get different atomic arrangements. It just shows you how complex water is inherently.
So what are the main types we usually talk about, especially when comparing Earth and space?
Well, broadly, you can think of two main categories. First, there's crystalline ice. That's what we have here, mostly.
Like snowflakes.
Exactly like snowflakes. Atoms arranged in a really neat, orderly lattice structure. Beautiful symmetry.
Okay. And other kind.
That's amorphous ice. And for the longest time, this was believed to be, the dominant form out there in space.
Why amorphous in space?
The idea was it's just too cold. Space is so incredibly cold. The thought was water molecules wouldn't have the energy to arrange themselves into those neat crystals, so they'd just freeze instantly in a jumbled, higgledy-piggledy mess.
It's a kind of frozen jumble.
Yeah, a frozen snapshot of liquid water's disorder, essentially.
Yeah.
That was the core belief for, well, a very long time.
Okay, so that's the long-held assumption that this new research is challenging.
Precisely.
So what exactly did they find? How is it turning our understanding upside down?
Well, instead of being this totally disordered, frozen collection of molecules, it now looks like there are repeating patterns.
Repeating patterns, like ordered structures.
Tiny ones, yes. Tiny crystals, just a few nanometers across.
Nanometers. Okay, really small.
Very small. But they seem to be embedded within what we always presumed was just this perfectly jumbled, amorphous state.
And that's the big surprise, right? Because everyone thought space was just too cold for any crystals to form.
Exactly. That's the key shift. The prevailing wisdom was, like you said, it's just too cold, not enough energy for molecules to find their ordered places.
So if that was the thinking, not enough thermal energy, what does this new finding suggest about that principle? Is it wrong or just incomplete?
That's a great question. It suggests things are more nuanced. It doesn't necessarily mean the basic principle of needing energy for crystallization is wrong, but maybe there are other pathways. Or perhaps even at these incredibly low temperatures, there are subtle energy dynamics, or maybe the way water freezes directly from vapor plays a role. Something allows for some local ordering.
Pockets of order in the chaos.
Kinda, yeah. It adds a layer of complexity to how we think about crystal formation in these extreme cold environments. It wasn't the simple open and shut case we thought it was.
That is fascinating. And Michael Benedict Davies from University College London, one of the researchers, he summed this up pretty powerfully, didn't he?
He did, yeah. He put it very clearly. He said, we now have a good idea of what the most common form of ice in the universe looks like at an atomic level.
And that resonates because...
Because for so long, that good idea was based on the assumption of disorder, complete randomness. Now, they actually have evidence painting a much more detailed and frankly surprising picture of what's going on down there at the atomic scale.
Right. And connecting this to the bigger picture, Davies also pointed out how crucial ice is.
Yeah, he noted it's involved in many cosmological processes.
For instance, in how planets form, how galaxies evolve, and how matter moves around the universe.
Exactly. So if you misunderstand the fundamental nature of that ice, you potentially misunderstand those huge cosmic processes too.
Yeah.
Getting the ice right is, well, pretty important.
Absolutely. So given how surprising this is, the big question becomes, how? How did they figure this out? How do you peer into the atomic structure of cosmic ice?
Right. Well, it wasn't easy. It was a really careful combination of sophisticated computer simulations, and some clever real-world experiments.
Okay, let's start with the simulations. What did they do there?
They basically created virtual boxes filled with water molecules, and then they froze them, computationally speaking, down to extreme temperatures like minus 120 Celsius, which is about minus 184 Fahrenheit. And crucially, they did this at different rates of cooling.
Ah, so how fast they froze it mattered.
It seemed to. They found that these different freezing speeds produced different mixes, different proportions of amorphous ice and crystalline ice.
Interesting. And did one particular mix stand out?
Yes, the proportion that best matched up with previous actual X-ray analyses of what was thought to be amorphous ice from space, that mix was around 20% crystalline and 80% amorphous.
20%. So even the simulations were hinting that maybe it wasn't purely amorphous.
Exactly. That was a really significant clue from the computer models. It strongly suggested there was some hidden order lurking in there.
Okay, so simulations hint at this hidden 20% order. What was the next step? Did they try to recreate this in the lab?
They did. They moved on to experiments designed to mimic space conditions more directly.
How do you mimic space ice formation?
Well, think about how water freezes in space. Often it's not like liquid water freezing, it's water vapor.
Right. Gas.
Gas molecules hitting a really cold surface like a speck of cosmic dust or a bit of rock and freezing instantly, directly from vapor to solid. It's called deposition.
Okay.
So the researchers did that. They deposited water vapor onto a super cold surface in a vacuum chamber, letting it freeze on contact.
Got it. Any other methods?
They also tried another approach. They took regular ice, like ice we know, and crushed it under high pressure, but extremely cold temperatures. This creates a different kind, a higher density form of amorphous ice.
Okay, so they have these different lab-made amorphous ices. What then?
Then came the crucial part. They took each of these samples, and they gently warmed them up.
Warmed them? Why wouldn't that just melt them?
Not necessarily melt, but warm them just enough so that the molecules would gain enough energy to rearrange themselves if they had some underlying tendency or structure to begin with, enough energy to form crystals.
Ah, okay. So if it was truly random, maybe nothing much would happen, or it would happen uniformly.
Kind of. But this ties into another fascinating idea, this concept that ice can sort of remember its previous structure.
Ice has a memory. That sounds wild. What does that mean?
It's about how the atoms, particularly the hydrogen atoms, are oriented relative to each other. Even as conditions change, like warming or pressure shifts, there can be a memory or a preference for certain arrangements based on how the ice originally formed or its history.
Like a molecular fingerprint.
It's a good way to put it. A molecular fingerprint.
Wow.
And this memory was key because when they warmed the samples,
What happened?
the way the ice structure changed, the way it reorganized as it warmed, was different depending on how it was initially made.
Different how?
They observed distinct structural differences. If the ice had been truly 100% amorphous, totally random, you'd expect it to behave in a more uniform way upon warming.
But it didn't.
It didn't. The specific changes they saw could only be explained if the starting amorphous material already contained these hidden, tiny crystalline regions.
The memory revealed the hidden crystals.
Exactly. The warming process allowed those pre-existing structures, that hidden 20% perhaps, to become more apparent, to influence the reorganization. It was strong experimental evidence.
Wow. Okay, so putting the simulations and the experiments together, this sounds like a pretty solid case.
It really does.
What's the biggest takeaway then? What does this mean for our understanding of water out there in the cosmos?
Well, even though these experiments happened on Earth, they provide really strong evidence that the most common form of ice throughout the universe isn't purely amorphous. It likely contains these tiny regions of crystalline order.
And that changes things how?
Fundamentally, it redefines our picture of water in space. And since water ice is so critical, I mean, it's involved in building planets, it affects how galaxies evolve, how material moves around. Understanding its true nature is vital for all those areas.
It's like finding out a key ingredient in your recipe isn't what you thought it was.
Precisely. It could change the whole outcome.
Christoph Salzman, another researcher from UCL, he had a great quote about this contrast between Earth ice and space ice.
He did. He pointed out how ice here on Earth, with its beautiful snowflake symmetry, is actually kind of a cosmological curiosity because our planet is relatively warm.
Right, we see the ordered stuff easily.
Yeah. And he said space ice was always seen as just a snapshot of liquid water, that disordered arrangement, frozen solid. Our findings, he said, show this is not entirely true. It's a simple statement, but it carries a lot of weight.
Definitely. And it doesn't stop with just ice, does it? You mentioned this might have implications for other materials.
Absolutely. This research kind of opens up a bigger question about amorphous materials in general, things that lack that neat crystalline structure.
Like what kind of materials?
Well, a great example is glass, or specifically the glass fibers used in fiber optics.
For transmitting data, internet?
Exactly. Those fibers need to be incredibly pure and perfectly amorphous to work efficiently to transmit light signals over long distances without scattering or loss.
Okay.
But what if those materials, like the space ice, aren't perfectly amorphous? What if they also contain tiny, nanoscale crystalline imperfections we didn't know about or couldn't easily detect?
That could affect their performance.
It could. And maybe, just maybe, if we understand this better, if we could find ways to remove those tiny crystals or control them, perhaps we could make those fibers or other amorphous materials used in technology perform even better.
So understanding cosmic ice could lead to better internet cables.
It's a potential long-term connection, yeah.
Yeah.
It raises really fundamental questions about material science, how we define and understand disorder at the molecular level, and what its consequences are.
It really makes you reevaluate things we take for granted.
It certainly does.
What an amazing journey from the vastness of space down to materials science. As we wrap up this deep dive, what's the main aha moment you hope people listening take away from this?
I think, for me, it's the sheer wonder of discovery. That something we thought was so simple, so understood, like frozen water in space,
The most common form.
the most common form,
Yeah.
actually holds these unexpected, intricate, hidden structures. It really shows that even in the coldest, seemingly emptiest parts of the universe, there's this surprising complexity, this hidden order,
It challenges our assumptions.
deeply.
Yeah.
And it reminds us there's always more to learn, even about the basics.
Yeah, it really makes you wonder, doesn't it? This research, it was published in Physical Review B, it makes you think, if ice, something we thought we had figured out, holds these kinds of secrets, what other fundamental materials or maybe even processes we think are simple might we be fundamentally misunderstanding?
Right. Where else is there a hidden order we haven't seen yet?
Exactly. What other supposedly impossible things are just sitting there waiting for us to find the right way to look? And how could those discoveries change not just our view of the cosmos, but maybe even the technology we depend on every single day?
It's a great thought to ponder.
Definitely something to keep that curiosity